Right. Okay. Maybe we start. It's 9:01. So good morning, everybody. Hope you had a good sleep. Welcome to the second session of sea ice. So today it's snow and techniques, and it's myself and Sinead Farrell who are doing the session. And again, we have very interesting talks today from Nathan Kurtz, Jack Landy, Florent Gandier, Henriette, and Rosie Willett. And we will start with Nathan. So he's from NASA Goddard Space Center, and he has been involved in CryoSat 2 also since long time. He also developed an own CryoSat 2 ice thickness and freeboard product. He was involved in lots of IceBridge campaigns and Calval activities. And his talk today is about the incorporation of surface roughness and snow depth into CryoSat 2 sea ice thickness retrievals and the assessment with IceSat 2. And yeah, Nathan, so it's yours now.
Okay, thanks, Robert. It's 3 a.m. for me, so I'll try to be as coherent as possible, but we'll see how this goes. Let's see. Okay. As Robert mentioned, I'll be talking about incorporating surface roughness and snow depth into CryoSat 2, seeing how that influences the retrievals of sea ice thickness, and then again what that means for comparison with data like IceSat 2. I'd like to acknowledge my co-authors, or people who've helped contribute to this work pretty greatly, especially those in the NASA Goddard Spaceflight Sea Ice Altimetry group. So Stephen Fons especially, we've worked pretty closely together on this. Then also Marco Bagnardi, Rachel Tilling, and Alec Petty. Okay, so what we've worked on quite a bit is using a physical model to model the CryoSat 2 waveform, and then building our retrieval based on that. And so this was from a paper that I and others published in 2014. And so it attempts to model the CryoSat 2 waveform by modeling the transmit pulse shape, the impulse response, the surface height distribution, and also the volume scattering through the snow layer and the ice layer. And so I'll be talking more about these two aspects in the CryoSat 2 model. And so the process uses the physical equations, and it has free parameters that we put into the model waveform, and then once those are run, a fitting process is run. It iterates on the initial guesses that we do give it to the free parameters, and as shown here in the movie, so the black dots would be the CryoSat 2 waveform, the power values received at those times. The blue line would then be the waveform that's being iterated on in fit, and then the tracking point of the waveform is then that dashed line. And so once the best fit waveform is found, these fit parameters then are what we would call the estimate of the true parameters, and especially things like the tracking point would probably be the most important one, but then other ancillary data like the surface roughness could be estimated from this approach. And so the idea with this is that with the physical model, we should be able to account for things like surface roughness and a snow layer within the snow layer scattering within the CryoSat 2 waveform. So that's what I'll talk about here. So briefly, I just wanted to touch on how do surface roughness and snow depth impact the actual waveform. So these are just images of simulated CryoSat 2 waveforms with different roughness values. And so what you can see again, the time equals 0 would be where you would track the waveform. What you can see is that the waveform gets broadened as you'd expect with the surface roughness. Does impact the trailing edge and the leading edge in different ways. And so here you can see the trailing edge gets broadened just a bit, the leading edge gets broadened just a bit, and the trailing edge gets broadened significantly more as the roughness increases. Some interesting research that's been done since the publication of my initial paper has been just what is the roughness that we could expect over sea ice. And so Jack Landy published an interesting paper showing that a Gaussian surface roughness is probably not appropriate, especially as the for sea ice, as opposed to again a Gaussian that had been used prior. And so this is interesting how it affects the actual waveform if you use a Gaussian or a log normal surface distribution. And again, especially where you would track the waveform point. And so just show two simulated CryoSat 2 waveforms with different values of the surface roughness for a Gaussian and a log normal. And so as the roughness is lower, then a log normal tends to a Gaussian distribution, as opposed to as it gets larger, that's when you see that skewed difference. And so what that tends to lead towards is quite a bit difference in the waveform leading edge, which is really important for where you would place the tracking point. So surface roughness definitely has an impact on the actual waveform. So next I'd want to move to the snow depth and the snow depth term. So snow is has an interesting way that it affects the waveform. And it broadens the waveform as we'd expect, especially the leading edge. But what it's really dependent on is what's the actual backscatter between the snow and the ice surface. And so these are some plots from a paper that Stephen Fons and I published a couple of years ago, trying to fit CryoSat 2 waveforms in the Southern Ocean. The black dots are the CryoSat 2 waveforms. But then simulating or running the model with different relative backscatter between the snow surface and the ice surface, and that's shown here. These different colored lines, and the backscatter there was taken from two different IceBridge radars: the KU band radar, which overlaps in frequency with CryoSat 2, the IceBridge Snow radar, which has a significantly lower frequency, and then the original estimates that I had used for a difference between the relative backscatter between the snow and the ice layer in the 2014 paper. And so snow, again, isn't as simple as roughness, where you increase one value and the whole of the waveform changes. Again, it's really dependent on what is the actual depth of the snow, the roughness of the surface, and then the relative backscatter between the snow and the ice surface. So, but the overall effect is to broaden the waveform. Some of the big unknowns, especially when we started out on this path, was obviously how does that relative backscatter between the snow and the ice surface change, especially spatially and temporally. I think we've gotten really good data from Mosaic in the past year towards that, so making good progress there. Where this is a really big unknown is in the Antarctic. We haven't really collected the data for that at this point. Okay, so in terms of the research in this, there's two different experiments that we wanted to run to see, okay, we know that surface roughness and snow depth have an impact on the waveform and what we're tracking. So how do we go about improving this when we have some knowledge of these? So the two experiments that we took were one, just looking at how the waveform is initialized with regard to snow depth and surface roughness. trying out different techniques for initializing the waveform, and then seeing if that improves some of the relative metrics, like in comparison to other data sets. And so to do that, just use the original fitting method from the 2014 paper, which is pretty simplistic. It didn't actually solve for the snow-ice interface. And so it didn't account for any scattering from a snow layer. It had a crude initialization for the surface roughness. We just fed it a starting value and then see where the solution went. The problem with that is that the actual solutions that come out can actually be pretty sensitive to how you initialize the fitting routine. So the closer you can initialize the fitting routine to the actual values, the better it tends to perform, but that's kind of a circular argument. So what we want to do is, again, initialize it as close as we can using information that's actually contained in the waveform. So again, just for this kind of experiment, took a simple approach, introduced scattering from the snow layer, but taking snow depth and density data from, or snow depth and density data from the Nososum snow model. Again, moving to this log normal surface roughness because that is expected to improve the behavior here. And then again, just seeing, okay, can we better initialize the model fitting procedure using lookup tables based on the widths of the waveform leading and trailing edge to fit the model here. And then call this a version 2 of the waveform fitting method. So just a couple brief comparisons, looking at IceBridge data from, this is just one season that had overlapping data with IceSat2, but I'm just showing the IceBridge data here. So just some maps of the IceBridge data, the thickness difference from IceBridge and the two different methods. So can see that just initializing the waveform fitting method did make a difference in the thickness retrievals and the thickness difference with IceBridge. The means in this approach were similar, pretty close to IceBridge. I think they were within about 20 centimeters, but the correlation did improve in this experiment. But looking a bit more broadly, tried to compare this with IceSat2. So feeding IceSat2 with the same Nososum snow depth and density data, and then the IceSat2 freeboard and getting sea ice thickness that way, putting those into the CryoSat2 solution again, and then looking at the differences over the 2018 to 2019 growth season. And so what we found just initializing the waveform differently is that overall it did seem to improve the comparison. And so the thickness fields, especially in the fall, the November time period, compared pretty well, but we do see some large spatial patterns in the differences. So it's not just a random, it doesn't appear to just be a random error, but much more spatially correlated. So, but this was just an experiment which was run, okay, if we initialize the model better, do we get some improvement? Yes, it does appear so, and again, in terms of the mean differences and the correlations, but there's actually another way to improve this. So to improve this separately, we looked at a different approach, and this is work really led by Stephen Fons, and we published a paper attempting to do this in the Antarctic from a paper in 2019. And so what this does is attempts to solve for both the snow air and the snow ice interfaces within the model. And for these experiments, we switched to a log normal surface roughness distribution, initialized the model with a climatological, or a guess at a climatological snow depth for the Antarctic, the Nososum model for the snow depth for the Arctic, but assumed a constant relative backscatter between the snow air and the snow ice interfaces. So the advantage with this is that we can solve for the snow air and the snow ice interface and potentially get the snow depth in the freeboard. So to do this, though, we took a different approach for comparison. Instead of just starting out the broad scale, we were inspired by the Cryo to Ice campaign and in looking for overlapping tracks within the Southern Ocean. And so here's just a plot of how we attempted to do this using data that existed prior to Cryo to Ice. So there actually were some overlapping tracks that happened, especially in the Southern Ocean prior to Cryo to Ice. And so again, here's just the criteria. And we found 179 overlapping orbits. And we selected 2 of those that had sufficient amount of data with IceSat-2 and CryoSat-2 over long tracks from October and September of 2018 and 2019. And so here's the tracks on the map. And again, the overlapping orbits that we found. So just looking at this on an orbit level with the comparison. So the green dots are the individual IceSat-2 freeboards, and then the purple dots are the CryoSat-2 freeboards, and then looking at the running mean. And so overall, we found a pretty good agreement with this from the track from September of 2018. Very small mean difference, and then a pretty good correlation of 0.77 here. Less agreement in the track from 2019. You can also see here, though, that there are differences due to the spatial coverage of the data. And this is all published or soon to be published in a paper that Stephen Fons has led in Earth and Space Science. And so showing another figure from that paper as well, moving beyond the orbit tracks, but looking at monthly comparisons for the entirety of the Southern Ocean, found pretty good agreement with this approach. So we call it the V2. From our original paper in 2019, we used V1. But again, looking at improving some of the physics of the retrieval, especially looking at like a log normal surface distribution and how we initialize the snow led to this V2. And so again, overall, with this approach, we found pretty good agreement in the Southern Ocean. So here's the histograms of the snow freeboard retrievals from the 2 methods. And they agree pretty well. And then here's the scatter plot. So small mean difference, pretty good correlation for this particular month. For a number of the months, we did find pretty good agreement between CryoSat-2 and IceSat-2. Less agreement in the fall, but that's discussed in the paper.
Sorry, just one minute left.
Oh, okay. I'll rush through this quickly then. For the Arctic, we also compared the same method. Again, seeing does this approach work well for the Arctic. So again, this is just one representative month. We did find pretty good mean difference, I'd say moderate correlation. We have broken this down into comparing the snow freeboard with, say, IceBridge from that, or from a time period. I'll skip over this, and as well as the ice freeboard snow depth. And so again, what we found in comparison with the IceBridge data is that we are able to retrieve snow depth, ice freeboard, and snow freeboard pretty favorably. But really, just to sum up, we do have a bit more work to do. So we have these 2 different methodologies that we're going to try to blend in the future. So the better initialization of the waveform just from the waveform characteristics, especially with regard to surface roughness and snow depth. But then again, increasing the complexity of the model fitting. Again, seems to work pretty well for the Southern Ocean, and then trying this more for the Arctic. But I think what's really going to be key for the Arctic is the cryo to ice comparisons, because that'll give us first look at, in detailed look at how this technique is doing, especially for the Arctic. Okay, that's it.
Great, thank you, Nathan. Appreciate that, lovely talk. We do have one quick question. Actually, there's a couple of questions in the chat, maybe you can answer later if you have time, but the very quick question that I think will be easy to answer comes from Einar Olesen. Has anyone tried linking the roughness observed by CryoSat to aerodynamic roughness? So you touched on that, but you could just say something a little bit more about that. Thank you.
Not to my knowledge with the CryoSat 2 data. I know it's been attempted with IceBridge data. I think there were some, I'm struggling to remember some of the other studies that were done. I don't think they were done with CryoSat 2 though. It would be an interesting problem. I mean, I think the roughness that we can retrieve with CryoSat 2 probably has some relationship to the aerodynamic roughness, but yeah, I'm sure there'd have to be something worked out there. I think they're at different scales of roughness there.
Okay, thanks, Nathan. And now we have our next presenter, which is Jack Landy. He's actually now also based in Tromsø. He's just next door to me. And so he will present about how do surface roughness and radar penetration affect Pan-Arctic snow depth derived from multi-sensor altimetry and physical waveform modeling applied to CryoSat 2 and Antarctica SARAL with the comparison to IceSat 2. Jack, it's yours.
Thank you, Robert. And many thanks to Nathan for introducing some of the topics that I'll be talking about here as well. And we can let Nathan get back to bed if he'd like to. So yeah, I'm going to be introducing some of the work that we've been doing for the ESA Polar Plus Snow on Sea Ice project. And as Robert mentioned, I'll be discussing physical waveform modeling applied to the main event here, which is CryoSat 2, and also to Antarctica with comparisons to the latest IceSat 2 data. So the ESA Polar Plus Snow on Sea Ice project is a European consortium project led by UCL, but involving many partners across Europe, including Lagos, the University of Tromsø, where I'm now based, as Robert mentioned, FMI, RV, and the University of Leeds. And the goals of this project are to better understand the snow depth penetration from laser, Ka and Ku band radar altimetry measurements as a function of the different properties of snow on Arctic sea ice, to then use this better understanding to generate improved multi-sensor snow depth products. And hopefully then with these improved products and better constraints on uncertainties to demonstrate the impacts they have for climate and operational applications in the Arctic. And then finally, to produce a scientific roadmap for ESA's future Earth observation satellite missions, including CRISTAL, to help address knowledge gaps of snow on Arctic sea ice. So the basis for this project are two main methods that were developed by members of our consortium a few years back. The first of these we call the calibration method. This is the dual altimetry snow thickness product led by Isabel. And the authors here, they used CryoSat 2 and Antarctica freeboards, radar freeboards, and these were then calibrated to the snow ice and the air snow interfaces respectively by using coincident airborne observations from Operation IceBridge. So based on the peakiness of the radar waveforms and relating that to the roughness from IceBridge, the two interfaces, snow ice and air snow, were calibrated to the right places to account for penetration and roughness biases. And then the alternative method, which we call the bias correction method, this is the Altimetric Snow Depth product from Kevin Guerrero, Sarah Fleury, and Florent Garnier. For this, because CryoSat 2 is using SAR processing and Antarctica uses more conventional pulse-limited processing, they have different footprints. The two sensors have different footprints. So by converting CryoSat 2 to a pseudo LRM, pseudo low resolution mode, the authors here were able to produce similar footprints between the sensors and account for roughness biases that way. And you can see in the plots at the top that both of these studies were able to produce realistic Pan-Arctic snow depth estimates, thicker on the multi-year ice north of Canada and thinner on the marginal seas. And they were also able to, if you can see my mouse here, note some of the accumulation in the Chukchi and the East Siberian seas that we'd sort of expect through the season. So in the course of Polar Plus snow on sea ice, one of the work packages we want to develop prototype products and to validate them. And some of the work that I've been leading here is to apply physical radar waveform modeling to these two sensors, CryoSat-2 and Antarctica, in LRM and SAR modes. And by doing this, we want to see whether the waveform simulations themselves might be able to account for some of the snow ice surface roughness biases or issues, so that we don't have to then calibrate them or correct for them afterwards. So we've applied this to CryoSat-2 and to Antarctica, and then compared to IceSat-2 total freeboard estimates of the snow surface freeboard. And we want to see whether the penetration biases remain. And it's important in the course of this work to not really think of IceSat-2 necessarily as validation data for the other sensors, but more it's an intercomparison between the three sensors. So the physical waveform model that we've been using is the facet-based radar altimeter echo model, which I developed with a few colleagues a couple of years back. And this model uses triangular meshes of the snow or the sea ice surface topography as the basis to perform integrations of the radar altimeter waveform. So what we can do is we can use actual laser scanner data of the snow surface or the ice surface topography and perform the simulations that way. So for example, here we've got some Operation IceBridge laser scanner data. This is a SAR footprint where we have a coincident CryoSat-2 echo. And in the bottom right, we have our modeled echo in blue. And then we've split the contributions, estimated the contributions from different scatterers within the footprint. So the snow ice interface roughness, the snow surface and the snow volume scattering, and reflections from leads. And during the course of this work, looking at the IceBridge data, we found that generally this log normal model for the roughness, as Nathan introduced, did a better job of characterizing the airborne laser scanner data in comparison to the Gaussian model, which has been traditionally applied in analytical waveform simulations over the ocean. So in the next part of the work, which was led by Alex Petty, we split up Operation IceBridge data in 2013 and 2014, including laser scanner data and the radar data, into sections that had about the same footprint as CryoSat-2. And we then fit these two different roughness models to our radar and laser data. And we found that most of the time, especially over multi-year ice, the log normal did a better job of characterizing the sea ice surface roughness distribution. And so this kind of informed our waveform simulations that we've been doing more recently. So that's what I'm showing here. On the left, we have a virtual statistical snow or sea ice surface roughness. So we don't have to use actual laser scanner data. We can create these surfaces artificially, many thousands of iterations. So this is a log normally distributed surface with a roughness of 50 centimeters. And then in the middle and on the right, we have the CryoSat SAR echoes and the Antarctica LRM echoes with these different roughness configurations. So these are idealized echoes from many thousand simulations. And the key thing to note here, which builds on what Nathan was talking about, is that 0 here is our mean level of our sea ice surface. And so the point at which we should be retracking the waveform is where it crosses 0 time here. And you can see that it varies quite a lot depending on the roughness of the surface, both for the CryoSat SAR echoes and for the Antarctica. So we build up a set of lookup tables from thousands of these simulations, and then we use these to fit actual CryoSat and Antarctica. And that's what I'm showing here. On the left, we've got a characteristic roughness sea ice surface with a standard deviation of 54 centimeters and our retracking point at around 70%. And then our lead has a retracking point right up towards the peak with this really specular return. And then for Antarctica Saral data, on the left again, we have our characteristic sea ice echo with our retracking threshold at about 30% here, and then the lead, the retracking threshold is right up at the peak, specular return again. And so we've applied this to retrack all of the Antarctica data between November 2019 and April 2020 to get estimates for the radar freeboard from Antarctica. We've done the same for CryoSat 2, and then we also have the IceSat 2 data, and that's what I'm showing here. This is December 2019, CryoSat, Antarctica, and IceSat 2. And encouragingly, we find that the Antarctica retrieved radar freeboards are more similar to the IceSat 2 laser freeboards than they are to the radar freeboards. For these waveform simulations, we're simply assuming with Antarctica that we're retracking the air-snow interface. So if we do find any differences to the IceSat 2 data, then we might, that assumption is false. But in this situation, we find strong similarities. And we get this gradient of thicker to thinner radar freeboards from Antarctica between the multi-year ice north of Canada out to the margins, but maybe it doesn't quite capture the thinnest ice that we see in IceSat 2. And we also see this circulation of thicker multi-year ice out into the Beaufort Gyre from all three of our products, which is great. This is the same thing for March 2020. We see a thickening with all of our freeboards, which is also good news. And in this situation, we start to see what is apparently an underestimation of the Antarctica radar freeboards, particularly over first-year ice in comparison to the IceSat 2 data. But generally, in the multi-year ice zone north of Canada and in Fram Strait, we're getting pretty thick radar freeboards. So the next thing we've done is to derive estimates for the snow depth by taking Antarctica minus CryoSat 2 or IceSat 2 minus CryoSat 2 and making corrections for the delayed wave propagation through that snowpack. And that's what I'm showing here. And then on the right is the difference between IceSat 2 laser freeboards and Antarctica radar freeboards. So the difference map on the right, we see this kind of characteristic salt and pepper pattern, but not really any systematic differences in any region. And the snow depth maps appear very similar. We're getting a strong gradient between the multi-year ice and the first-year ice zones. These are the histograms of the differences for the areas that coincide between all three sensors. So the freeboard distributions are quite similar between Antarctica and IceSat 2, but we're not appearing to capture the thinnest freeboards with Antarctica. This may be to do with the noise in the Antarctica range measurements, or it could be to do with our waveform classification scheme, how we're separating ice flows from these. The snow depth distributions are pretty similar, and so we get a ratio in the freeboard differences between Antarctica and IceSat 2 around 1. For March 2020, we see an increase in the snow depths derived by both techniques, but the difference map on the right, you can start to see this systematic underestimation of the freeboard by Antarctica in comparison to IceSat 2. You don't see this so much in the multi-year ice, and we see also Antarctica overestimating IceSat 2 in some of these thin ice marginal zones. And the distributions with the freeboard, the first thing that we can note is that the Antarctica radar freeboard distribution is unimodal, whereas the IceSat 2 and the CryoSat 2 distributions are both somewhat bimodal, reflecting the differences between first-year ice and multi-year ice. So Antarctica may not be able to capture the full dynamic range of snow surface elevation variability across the Arctic. The derived snow depth distributions are quite similar in width, but they are systematically shifted by an amount. And so we get a freeboard ratio between Antarctica and IceSat 2 of about 90%. This is what we get when we apply IceSat 2 minus CryoSat 2 to retrieve snow depths over the whole season. And the first thing I point out here is this grey contour defines all of the snow that is below 5 centimetres. And I found this really encouraging because in situations where we expect the snow depth to be really low over newly formed sea ice, and so the IceSat-2 and the CryoSat-2 freeboards should be really similar, then they very often are, which is really, really encouraging. But we also then see the snow depth increase over all ice types over the course of the season, and we see the strongest accumulation occurring in the Chukchi and the East Siberian seas, which has been noted before by Ron Kwok and others. These are the time series of those plots for IceSat-2 and for Antarctica. Because the IceSat-2 laser freeboards increase at a faster rate over the winter than the CryoSat-2 radar freeboards, then you get this accumulation of snow over the course of the season, which is what we expect based on observations. But with Antarctica, the radar freeboards are increasing only marginally faster than the CryoSat-2 radar freeboards. So generally, there's not much seasonal variability. The mean line is shown by the bold line, with the standard deviation showing the Pan-Arctic standard deviation. And we see the wider distributions for Antarctica in comparison to IceSat-2, but similar magnitudes between the two. And then the final thing I want to note here is with the physical waveform fitting technique, as Nathan talked about, we can retrieve the surface roughness as another parameter beyond just the range which we need for the freeboard. And so on the left is the retrieved surface roughness from Antarctica in January 2020. And you can think of this as the roughness of the scattering surface, so a combination of snow surface scattering and some volume scattering. And what we've done on the right is plot the relationship between the surface roughness over the entire winter season, 2019 to 20, versus the difference between Antarctica and IceSat-2 freeboards. And because there is a systematic relationship here, this tells us that this bias between the two sensors is related to the surface roughness. What this suggests is that either our waveform simulations for Antarctica and perhaps also for CryoSat-2 may not be fully characterizing the role of roughness. It may also be related to the waveform classification scheme. We might be discarding too many thin, smooth ice flows from our Antarctica data. And it also might suggest that snow depth and roughness have some redundancy, which has been talked about previously. In places where we measure thicker snow, we're likely to measure rougher ice and vice versa. And so it's hard to really differentiate between the two. So just to summarize, we've applied this physical waveform modeling approach to CryoSat-2 and to Antarctica over the November 2019 to April 2020 winter season. Our cooler IceSat-2, CryoSat-2 snow depths exhibit really realistic seasonal evolution of magnitudes, although we haven't yet looked at validation against independent observations. But the KUKA, CryoSat-2 Antarctica snow depths lack seasonal variability. The K and LRM observations from Antarctica may not be able to capture the full dynamic range of snow surface variability, and there may be some partial penetration into the snow cover, especially over first-year ice at the end of the season. And we find the freeboard differences between Antarctica and IceSat-2 depend closely on surface roughness. And so in future in the Polar Plus Snow on Sea Ice projects, we'll be intercomparing with existing methods, for example, dust, ASD, which Florent will talk about momentarily, and the passive microwave data, and also a comprehensive set of airborne and ground validation data. And just finally, I want to say a huge thanks to the folks at ESA for all the sterling work they do with the CryoSat-2 mission. And I've been really lucky myself to benefit from ESA funding through Polar Plus, but also through the cryosphere element of the Living Program.
Okay, thank you, Jack. Appreciate that. There's no questions in the chat, but I do have a quick question myself, just very briefly. So you mentioned the differences between IceSat-2 and Antarctica. and attributing that to the contributions of surface roughness. But could you speak a little bit about the retracking errors and the potential for that to be one of the contributors towards those differences?
Yeah, it's quite difficult to decompose this, and it's something that I and others as part of the group really want to look at in the future. It might be that we are not accounting for the roughness properly in our retracking. So it might be that we have some kind of human error in our simulations that's leading to issues with the retracking, or it could be that we've accounted for the roughness fine and the rest of the differences are related to other things. For example, Ka band penetration into the snow, and it's quite hard to decompose those two things.
Yeah, okay, thank you. There is another question from Stefan in the chat, so perhaps you could
Sure.
Answer that when you have time. Thank you, Jack.
Yeah, thanks, Jack. That was really interesting. So next presenter will be Florent Garnier. And so he's presenting on a similar topic. So it's about, and Florent is from Lagos, Toulouse. And his presentation is about the assessment of KU altimetric snow depth on the sea ice product. So Florent, it's yours.
Florent, when you have time, I think we need you to unmute.
Yeah, try to unmute yourself. Maybe you're enabled.
Okay, so while we're waiting for Florent, Jack, there was another question.
It's okay. Can you hear me?
Oh, okay, we have him. Okay.
So sorry, I couldn't click on the button. Okay, so you hear me? You see my screen? So sorry for the delay. So hello, I am Florent Garnier. I work at the Lagos laboratory in Toulouse on sea ice observation from altimetry as part of the ESA Living Planet Fellowship. This presentation is about the assessment of the ISD-KU altimetric snow depth on sea ice product. And the results I show here are based on a recent article and have been promoted by the ESA Polar Plus and CryoSat Plus Antarctic Ocean Project. I think it was good to have the presentation from Jack because he already introduced a lot of things about this presentation, so it will be easier for me. The bifrequency altimetric snow depth measurement is based on the difference of penetration between the Ka frequency, which is supposed to be reflected on the top of the snowpack, and the Ku frequency, which is supposed to be reflected at the snow and ice interface. Then the snow depth is simply the difference between the total freeboard of SARAL and the ice freeboard of CryoSat 2. These two freeboards are calculated from the same methodology based on pulse thickness classification and the TFMERA 50 retracking. Since SARAL and CryoSat 2 operates in different modes, they have a different footprint, as you can see on the figure on the left, and then the impact of the roughness on the signal is different. In order to realign the data, we use the CryoSat 2 pseudo-low resolution mode data. Then it is the ESA-GOP product, which is used for CryoSat 2. We use the baseline B until 2017 and the baseline C to go until 2019. Since the baseline B do not include the SARIN mode, the ISD product does not yet include SARIN data. However, we're currently reprocessing the baseline C pseudo low resolution mode data over the entire period, which also include 2020. So the product should include soon the SARIN zone for the two hemispheres. In addition, we also plan to extend the data in October for the Arctic, because currently in the Arctic, it is available from November to April, and in Antarctica from May to October. The data are in free access on the Aviso.is platform, but you can also send me an email. It is written on the bottom of this slide, and I will be pleased to send you a link to download the data. And it's also sometimes better to send me an email because updates might be available even if they are not yet on the platform. For today, the objective of this presentation is to demonstrate the consistency of this ISD data in both hemispheres by comparing with various other snow depth estimation. And finally, I will also say a few words about the impact of snow depths on the sea ice thickness. We first compare the ISD product in the Arctic, and apart from the climatology of Warren, there is only, at least to our knowledge, two other global snow depth observations. The first is the dust product, which is also a KAKU, but the methodology is a bit different. One main difference is that instead of using the low resolution mode data, they recalibrate the data on Operation IceBridge. And the other product is the passive radiometer, IMSR2 and IMSR-E product. But the main issue with this data is that the algorithm to compute snow depth is not adapted to multi-year ice, and then the product usually only provides data over first-year ice. But for our comparison, we have used a version of Rostowski et al. That use a different algorithm that allows to have snow depths over multi-year ice. But these data are only available for March and April, and also they use Operation IceBridge within the processing of this data. So then the figure present bi-monthly, March and April, snow depth mean maps calculated over the 2014 and 2018 time period. And the figure below indicates the interannual variability, which is simply the standard deviation between all the maps we used to construct the means. We can see here that the KAKU product, the two products have comparable spatial distribution, as for instance, the thick snow in the buffer gyre, and that they have nearly identical variability. And in fact, the deviation between these two products mainly seem to be some bias of about 4 to 6 centimeters. IMSR2 have also comparable distribution, but the data are much more smooth and they present nearly no variability except in the multi-year ice zone. But when we look a bit more accurately in IMSR2 data, we have identified noticeable deviation with the ISD in terms of magnitude and spatial variability. We have also compared with three models, Biomass, Nesosim, and the Mercator Ocean model. The figure on the left are the global mean between March 2013 and April 2019. In the middle, it is the mean annual variability, and on the right, the mean interannual variability. So even if there are some clear differences between the representation, in particular in terms of variabilities, we're quite happy to find good coherences between the pattern in ISD, Biomass, and Nesosim. And even if I won't have time to go in much detail here, there is a lot of much more information in the paper. Just note that in general, and also from the previous comparison, the ISD data are always a few centimeters lower than the others. Of course, except, as we can see here, for the Mercator model, in which we identified important snow depth underestimation. And I take the opportunity to indicate that we are currently working with Mercator to perform freeboard data assimilation. And we found that the snow depth model representation is very important, since the freeboard model equivalent is computed from the sea ice thickness and the snow depth. Then prior to data assimilation, a reparametrization has been done to improve Mercator model snow depth representation. And we also think that it could improve data assimilation performance to integrate snow depth information at the same time of the freeboard. It's a bit out of the scope of this presentation, but I think it also underlines that it's important to develop this kind of snow depth observation. We have also compared our data with some validation data. This figure presents a projection of the snow depth monthly gridded map along the OEB campaign of the 29th March of 2015. OEB data are in blue, the ISD data are in red, with its uncertainty in shaded red. In brown, it is dust. In grid IMSR2, there are the model data and also the Warren climatology, which is, as we could expect, strongly overestimating the data. We see quite good agreement with ISD, in particular in terms of long track variability. It's not always as good, but most of the time it's at least included within, Operation IceBridge is at least included within the range of ISD uncertainty. If we consider now all the Operation IceBridge between 2014 and 2018, we found good statistics for ISD with correlation of about 0.6 and no bias, which is quite satisfying. But note that we also found good correlation for dust and from AMSR2, which are in favor to the relevancy of this observation product. Statistics are a bit lower for the model, but still correlation of 0.5 are quite acceptable in the Arctic. We have also looked at the 2017 CryoVex mission, where the snow depth is evaluated from a carbon altimeter in blue and a laser altimeter in dark blue. Unfortunately, mainly because of the Saral orbit limitation to 81.5 degrees in latitude and the absence of the sarin mode in our data, we've only been able to look at one track, which is located in the Baffin Bay. And we found consistent results in terms of magnitude from IceB, which is included between the laser and the CAS snow estimation, maybe a little bit closer to the laser data. But the variability is quite different here. But it's important to remind that we are comparing some monthly means against some daily data. So there is, in any case, some error of representativity when you do this kind of validation comparison. One important advantage to this snow product is that we've been able to compute the snow depths in Antarctica, where we have compared with AMSR2 data, the Mercator model, and the GeoMass model. This figure is the same as before, global means on the left, annual variability in the middle, internal variabilities on the right side. And compared to the Arctic, the ISD product is much smoother, which contrasts this time with AMSR2. The GeoMass model has very large snow depth values that seem quite unrealistic, while the Mercator model performs much better than in the Arctic. I won't have time to go into much more detail, and basically it's quite difficult to analyze this data and the difference with the Arctic, mainly because there's a lot of things in terms of roughness or penetration that it should be really interesting to investigate, but there is a strong lack of validation data, and I think it's again the occasion to point out that we need validation data in Antarctica to be able to go a little bit further. One important limitation to the ISD data is that they are only available from the launch of Saral in 2013. And then if we consider the quite low variability we have found in this ISD product, we have constructed a first guess, quite simple, monthly mean climatology using all the data over the 2013 to 2019 period. And this scatter plot shows the comparison between this first ISD climatology and Operation IceBridge when we consider the 2009 to 2013 mission, which means where we didn't have some snow depth data from Saral. And actually we found quite good consistency with Operation IceBridge. It's much better than the Warren climatology, which is the scatter plot on the right, meaning that we could consider and we could use this snow depth estimation for at least the whole CryoSat 2 period. Finally, we have investigated the impact of the snow depth on sea ice thickness, or the level of uncertainty of the sea ice thickness, which is due to the snow depth. And the originality of the approach is that we consider the various snow depth solution as an estimation of the snow depth uncertainty. We can then compute an ensemble of sea ice thickness using all the different snow depth products, and the characteristics of this ensemble can provide statistics on the sea ice thickness uncertainty, which is due to the snow depth. It can be seen as a kind of equivalent of multi-model approaches, and this time series illustrates this ensemble by representing all sea ice thickness annual mean representations. From this ensemble, we then have for each month a series of snow depth maps from which we can compute statistics such as standard deviation or maximum deviation at each grid point. If we then consider, for instance, the month of April, as is the case in this figure, all the map over the 2000 and all the map over the whole period, We have at each grid point a series of statistics, and this is what we show here. On the top, this is the minima, the mean, and the maxima of all the standard deviation calculated over the whole period at each grid point. And on the bottom, this is the same, but for maximum deviation. I don't know if it's pretty perfectly clear. It's sometimes confusing to explain. But finally, if we consider the whole set of the sea ice thickness maps computed from the various snow depth solution over the whole period, we found a mean standard deviation of 20 centimeters for the sea ice thickness and a mean maximum deviation of about 50 centimeters also for the sea ice thickness. And we found also that higher uncertainty are mainly located in marginal zones. To conclude, the objective of this presentation was to present this Kayu ISD Snow Depth product. The objective was not to say that one product is better than one other, since it is difficult to have objective diagnosis for that purpose, but to show that the objective is to show that ISD is a relevant solution for snow depths that has the advantage of providing some information in Antarctica. We also show that a climatology could be constructed with this data. Here we've shown a first guess climatology that appeared to be relevant for the period of CryoSat 2, but we could imagine to use this data together with AMSR, AMSR2, or even with the Warren climatology to go back on the unvisitad period. I insist in the conclusion about the importance of snow depths for data assimilation and the fact that the synergy with model is, I think, very promising. For instance, to fill the gap due to orbit limitation or the lack of summer freeboard estimation. And that goes towards some perspective, because since we have more information about the snow depths, I think it's important to look at the southern hemisphere also. And in addition, we now have IceSat 2 now in both hemispheres that also provide very important information on the snow and give information also on the problem with the roughness and penetration as we've seen in the previous presentation. And to finish this study, I wanted just to argue in favor to the Crystal mission that should provide a long track Kayu snow depths in SAR mode, and then we'll be able to answer to many questions we have today in this data. So thank you very much.
Thank you, Florent. That was a very nice talk. Lots of interesting details here to dig into. I just remind to everyone participating that the chat is for questions to the presenters only. Florent, I have a quick question. You mentioned the need for additional validation data in the Southern Ocean. Specifically from an airborne perspective, what type of instrumentation do you recommend for further data collection?
I think there have already been some airborne mission like CryoVex and Operation IceBridge, but the thing is that I don't have access to the data, or I don't really know how to get this data, so maybe some people can help me. And I think to have this kind of forced snow depths, I mean Ka band like in CryoVex would be very helpful to characterize the snow depths in Antarctica, because we saw some differences with the Arctic, but for example, for the gradients, we have very smooth solution, but we can't really analyze that and know where does it come from. Is it a roughness which is different, to the snow densities and the snow physical characteristics which are different? And I think that the point which is the most important to answer, to be able to validate our snow depth data.
Yeah, okay, thank you. I think a very good point. And perhaps using a Ku band sensor in future surveys may assist as well. Mm-hmm. Okay, thank you. So Jerome Bouffard is saying that they plan to make all of the CryoVex data accessible through the Cryo2Ice portal. This is the logo for that. So keep an eye on the new portal, the Cryo2Ice portal, for some additional validation data. That's going to be really helpful. Thank you. Okay, Robert, back over to you. Thanks.
Yes, thanks. Thanks, Florent, for this presentation. So our next speaker was supposed to be Henriette, but she unfortunately was not able to give the presentation now. So therefore, René Forsberg from DTU, he will give the presentation on behalf of Henriette. And hello, René.
Yes, I'm sorry. Henriette had to go to the doctor, so I'll take that at short notice. I hope you can see my screen. And I will talk about the CryoVix campaign on behalf of Henriette. Of course, I'm René Forsberg, but I've been involved in the same campaigns for ages. I'll just add to the two comments in the chat that the CryoVix data are actually out. You saw Mark Drinkwater's latest remark. They might not be completely updated, but it's great if people can use it more. The co-author of this presentation, apart from myself, is Alessandro and Signe Hvidgaard and Tanja Casal. So what was the goals of the CryoVix campaign? Well, it was basically to understand and validate the satellite missions. It started with CryoSat, but it's also been Sentinel-3, been Antarctica. It has been lately, we also looked at the CryoSat-2 and IceSat-2 cross-calibration. We looked at the, also there was some lines we always flew since all the way we started 20 years ago, north of Greenland, for having detailed time series for specific sites. And finally, it's also proof of concept for new technologies, flying many different instruments over the years in preparation for future missions. And the whole concept is going from the satellite level, having the airplane, collecting data at the regional base on 100-kilometer scales, and then have teams on the ground. And there's been a lot of different people involved in these campaigns over the years. We have used a small aircraft, a Twin Otter, for 20 years, which originally was with Air Greenland. Now it's with Northern Air in Iceland. So it's been quite inexpensive campaigns, but of course not large like the IceBridge with many instruments, but very much ad hoc. When we started, we actually started before the launch of the first CryoSat. In 2003, there was a campaign joined with the APL folks, and we flew the APL radar. KU band radar north of Greenland and across the Greenland ice sheet. And there were a couple of more campaigns in preparation of CryoSat 2. Then during the 2010s, we had a total of 8 campaigns in the Arctic and 1 in the Antarctic with different goals and different things. But you can see on the tracks, they were typically starting in Iceland, going up to the North Greenland, going out in the Arctic Ocean, way out, operating also from Canada and Svalbard, and also on one campaign all the way over in Alaska, in the Beaufort Sea. And lately then also there came an opportunity for a campaign in the Antarctic, flying with the British Antarctic Survey out of Rotterdam, going both in the Weddell Sea and on the Antarctic Peninsula, a little bit deep into Antarctica along the Ellsworth Mountains. So a very broad set of data is there, and it's really waiting for the full exploitation on the science level. So here is basically a list of the different campaigns carried out over the years. The pre-launch with the D2P radar, and we had the European radar ESA-ESRIN being certified. Then, of course, after the CryoSat 2 launch, the first validation campaigns, the first fall campaigns in 2016, where we have both flew the KA and KU radar. As we already heard, it gives you an enhanced recovery of snow depths and enhanced recovery understanding of firn properties on the ice sheet. We had the spring campaigns, we had the first Antarctic campaign, and then in 2019, we had both a spring and a late summer campaign to underfly IceSat 2 and CryoSat also. We also at 2019 campaigns tested a new CryoSat radar. We had different radars, and CryoSat had the broadband radar, which was really a large step forward. 2020, we were supposed to go to Mosaic with coordinated flights along the Polarstern, that unfortunately had to be cancelled. This year again, we had a Cryo2Ice campaign, which we also had to cancel. And one of the main problems with the cancellations is that Svalbard, Greenland, Arctic Canada all have different corona rules, and it was really impossible to have access everywhere. We did have operations in Greenland, but we also had to have the other access points. So the next plans are really a 2022 Cryo2Ice campaign, probably in March, April, be coordinated with activities with the Canadians operating out of Eureka. and possibly also an Antarctic campaign. So the instruments we have flown over the years, the workhorse has really been a laser scanner, commercial laser scanner from Rigel near infrared, 1x1 resolution, typically about 300 meters swath width. Depends a little bit on your flight height. You can go up to 500 meters. And it's a near infrared beam. Then we had the original, the APL flight, APL radar, which is a KU band radar, then the Cirrus radar, which is now sort of retired. The company has gone bankrupt, but it still sits in our basement. And then in the later years, the Karen, which was a Ka band radar developed by Meta Sensing, and then 2019 onwards is the Crazy's dual frequency radar, which both has Ku, Ka band. And the advantage of having both the LiDAR and the two different radar bands on the same aircraft is, of course, you have all the data at the same time. Not that it always works, because the LiDAR still needs cloud-free or fog-free conditions. But of course, by and large, we got a lot of data. It's still sitting there, a lot of that, and quite a large volume also. Of course, the whole idea is that you have, in principle, the Ku band going to the snow ice interface, the Ka band maybe a little bit more in the snow interface, the LiDAR for sure to the snow interface, snow air interface, and then for the sea ice, you can recover the freeboard. That's, of course, theory, and there's a lot of mixed results from that. Here's a campaign overview where we have the different satellite underflights trying to hit the satellite at the same time as the satellite overpass is actually quite challenging. The satellite don't care about work hours, weekend closures, or day or night. So they're coming when they're coming, and just making sure we get underflights in near real time is quite a logistical challenge. We see we had IceSat-1 underflights, actually in 2004. We had Envisat underflight, and then a lot of CryoSat underflights over the later years. A couple of Sentinel flights, a couple of Saral Altica flights, and then 2019, two double IceSat underflights. And that was actually before Cryo to Ice. And there's more data on this in Farrell's and Duncan's poster number 125, where you see much more on the data here and how to do all this validation from both ESA CryoVix and IceBridge. But this has all been a lot of collaboration and teamwork. Over the years, we had a lot of cooperation with Arvi, with the iceberg, the snowbird, both in the helicopter mode, as you can see here, and lately with the DC-3 joint underflights of CryoSat, where both have DC-3, IceBridge maybe, CryoVix, and the satellite on top. Quite a feat to get that one happen. That happened at least in a couple of incidences, one from Alert. Then we also had the NASA JPL Glistin, which is a swath mapper, interferometric Ka radar, coordinated campaigns there, and a lot of in situ campaigns with different science groups. And that has been the typical thing of CryoVix, that ESA has coordinated the work, but the science groups and also to some degree our group has paid for their own other issues and salaries and so on. But there were Cambridge Bay experiments. 2016, we had camps north of Greenland, the Green Ice Camp. We had the US camp in the Beaufort Sea, the Apples, where there was a flight program. Various EU projects, Green Ice, Damocles, have also given coordinated data there. Then we had overflights of icebreakers like the Polarstern in a couple of incidents, and in Antarctica with the Shackleton, the ship there. And here's some examples. Here's some examples of flights from Polarstern with the helicopter EM. And here we have the laser measurements of the ice thickness also, or the freeboard, sorry, also. And you can see good coincidence, but you also see details in the way these different methods pick up the local details and the ridges and so on. So that's a lot of work. Where are we now, and what have we learned to this? Well, before the launch, of course, some issues were already clear. That there are big differences where you are in the Arctic. If you compare the laser and the radar, for instance, in the early campaign, you had difference in the mode depths. The laser typically gave a little bit larger freeboards than the radar, and that was known. It was also known that it was a function of penetration, and in the Greenland Sea, for instance, there were big differences, and in the Lincoln Sea, there were less differences with these things. As we get up in time, we see that the radar returns are better understood. But again, depending on the tracking and how we handle it, you get different results. And again, the papers here by Stefan and Pabilat, which outlines many of these results. With the post-launch campaigns, we then can go out and start looking what do we get with the different types of measuring freeboards from aircraft versus the measurement from the satellites. And these plots here, they basically show the ESA-ESRIN freeboard, the airborne laser freeboard, and the ATM freeboard in IceBridge compared to the ARVI freeboard determination for CryoSat. And you can see that I wouldn't say that the correlation is good, but there is a kind of correlation, and it just shows that this is a difficult game to get all these right. You can also here see some statistics, the correlation between the different issues down here, which is, for instance, the airborne LiDAR freeboard versus ARVI freeboard, airborne laser versus ESA freeboard, airborne ESA-ESRIN freeboard versus ARVI freeboard, ESA-ESRIN, Operation IceBridge. Correlation is there. It's not great. It just shows that it's a different game we are in. And there are mean differences, but there's root mean square error. So we are sort of on the 10, 20 centimeter level to really map these things on looking back on many of these campaigns. So the data are really still very useful for getting more information and better understanding. So what happened since 2017? We flew the dual frequency radars, so the Cirrus, the Ka band from meta sensing, and the LiDAR. How can we learn more? And here was a very large experiment carried out in 2017 from CFS Alert with both in situ teams and different sensors. And we also had a major experiment related to sea ice in the Antarctic campaign by chance. The Antarctic campaign was mainly designed to fly over the peninsula, but there was a coincidence that there was a team on the Shackleton ship in the Weddell Sea, and they did ground truths. And I'll just show a few things here. Here you can see in Antarctica, of course, a very complex picture, and the complex picture comes when you try to underfly CryoSat, and you have to do it a specific day, and if you get delayed by one day, the CryoSat will be a completely different place. So it's quite a game to get these things to line up. But you can see on the codes here that there was actually luck on many of these days to get either a CryoSat or IceSat, a CryoSat underflown, not IceSat. So here we're looking at the 2007 campaign from Alert in the Lincoln Sea. And here we had actually two occupations, two periods where we came to Alert. That was for historical or for practical reason. It came in two epochs, and early and a little bit later in May. And for instance, here in the first campaign on the northwest line out of Alert, there was a CryoSat line. And Christian Haas and his team landed on 10 different sites with Twin Otter, put out people and made sure that we really had the full history of the ice properties and snow depths and so on there. And a month later, there was another opportunity, a little bit fewer landings, but again, overlapping with CryoSat. And also IceBridge flew some of these tracks here also. So quite a broad data set to study here. Here's some example of this long line. What did we get in terms of the snow depths? The snow depths in the green dots are the measured values, either in the mean or in the modal value. The Warren is the climatology, and the blue is the NASA Operation IceBridge. And the white one, the white-yellow ones, is the Karan Cirrus. So Karan is the Ka band radar, Ku band radar combination. So quite large differences actually along some of the tracks. So again, that's food for thought and give you some more work. What is really going on here, and how can we improve these things? For the Antarctic, the experiment was carried out on one of the stops of the Shackleton. Here you see a picture of the Shackleton lying on the edges of the ice shelf. We had the overflights. There were people on the ground. And then you can look on the airborne laser scanner, minus the 80% retract the cirrus. What's the mean value for the snow depth and the standard deviation? Or get the same snow depth from the Karan minus a cirrus. So that's Ka minus Ku. And again, you see some differences, but it's in the 10 to 15 centimeter mean range, but quite a large difference also. Here is an example of some ground truth radar. I think it was Rachel who was there on the ground, measuring the ground penetrating radar 2 to 18 gigahertz and making various experiments with having a plate on the surface, a plate on the ice snow interface, and trying to really understand what's going on. Here's a student of Henrietta's who has been looking at some of these data, and also I guess it's Rachel herself also. You can basically see when you look on the reflection of this ground penetrating radar from the surface down to 20 centimeter. Well, you get peaks there around 14, 15 centimeter. And these are on 4 different locations. And again, it's quite consistent with the 15 centimeter we just measured. So there's a lot of potential to really validate the satellite determination of snow depths in some of these data. Going to 2019 was the first IceSat-2 underflight and CryoSat-2. And so different missions carried out, but the underflights were mainly out of Station North in Greenland, which is a very easy place for us to work from. There's also sea ice flights in the Baffin Bay underflying the CryoSat here, plus a little bit of work on the ice cap. These data are still not available. They are essentially processed, but there's been a little bit of delay to get the last details out. But they're coming. They should be there very soon. In 2019 spring, we of course had the underflight, a near coincident underflight of both IceSat and CryoSat and the airborne LiDAR. They were not perfectly aligned because it was not really cryo to ice time yet. But we can see here in this area north of Station North, north of Greenland, going up quite a large distance, 300 kilometers. Here we see the CryoVex airborne LiDAR count for the Freeboard, and the CryoSat count, and the IceSat-2 count. And again, you can see that the IceSat and the ALS from our campaign are pretty similar, but the campaign still catches the very thick, the higher ridges, a little bit more than IceSat can do. That's very obvious. But also that the model for CryoSat is a little bit shifted to thinner ice. After the CryoSat spring 2019, we actually had an opportunity to do a summer campaign. It was not really planned, but it was kind of an opportunity, so we just jumped at it. And that was the first demonstration at flying the CryoSat radar with the KU-KA broadband radar on board. On that summer campaign, there was a lot of, on the sea ice wise, of course, all the sea ice flows were full of water, and therefore they were reflecting, and they were basically the dominant part of the sea ice signal. So it's maybe not so relevant, but of course it's good to see how far can you push IceSat sea ice freeboard determination in the summer period. The big question is, of course, whether these lakes on the flows, are they connected to the ocean, or are they on the level of the flow? And that's something changing during the summer. And you can see a laser profile here. It looks a little bit weird. But what is happening is, of course, all the lakes, if it's quiet, the laser return go down, but they don't go back to the aircraft, so they get white, no return spots. But just under the aircraft, you get returns back up because of the mirror effect. So it's a little bit challenging to use these data, but they're very rich. And here you see some examples on the KU-KA band. There's some work being published right now by the CryoSat group on these experiments here. But again, a rich data set waiting for people to grab it and use it for more science. Okay, so what are the conclusions and outlook then? Well, we have a lot of data sitting at ESA, and some of that's still in our end, getting it ready. We had some delays, but the data are coming out now. It's coming at the ESA online at the link where Mark Drinkwater just showed it. The level 2 data processing is coming. Then we have the upcoming campaigns, which is the CryoVex Cryo to Ice campaign, March, April. And then we have beyond CryoVex, of course, Crystal is coming up. There's validation of Sentinel-3 and so on, possibly on the horizon. The last statement I'll say is thanks for your attention on behalf of Henrietta, and also show that this is teamwork. And if you look on these pictures, you will recognize some ESA officials, going along with us way back and currently. And also some of the team works here, and that's Sine, our co-author. She's also doing very much of the work involved here. So thanks a lot for listening in.
Wow, thank you, René. What a
Thank you.
lovely summary presentation of all the incredible activities that have gone on over, as you say, not just the last 10 years, but really the last 20 years. Incredible efforts. And yeah, just on behalf of all of us here, thank you to you and your entire team for all of this hard work. It's not easy. It's fun, but it's not easy being in the field. So thank you so much.
Oh, you're welcome.
From the point of view of future campaign planning, what would be the most important parameter or question that you feel we need to address, be it on land ice or sea ice moving forward?
Obviously, it's cryo to ice, both in Greenland, in the Arctic and the Antarctic, to really fully understand the snow depth issues, but also very much the role of the ridging and everything there. So I think we cannot get enough data there. On the ice sheet, on the ice cap sizes, of course, getting a full penetration understanding of the in the fern and the different fern properties. And actually, we did when we did the polar gap flight, which was a gravity mission, we also did flights around the South Pole in the deep interior Antarctica with the ESA-ESRIN. So getting these airborne campaigns way deep in is also important. But another issue is also that when you mobilize these aircraft anyway, why not go out and collect data in areas where we don't have data? And right now there's a move, for instance, in Antarctica to get some of the big glaciers and the sea ice in front and everything, get that fully understood, that system. And that could also be a useful thing. Finally, I would also say we should probably also make sure that we get the data out quickly, because our team at least is very small, and we've been working on a shoestring all the years. And we probably should do an effort to get a little bit more manpower into these things. Of course, it's a cost issue, but it's nice to get the data out. I must say that IceBridge was a great model that you fly and 6 months later the data are there. That was really the ideal situation.
Well, thank you, René, and yeah, kudos to Nathan Kurtz and his team as well on the IceBridge side. Okay, I hand it back to you, Robert, and the best presentation for last, perhaps.
Exactly. Yeah. Thanks, René, again. So yeah, we'll come to the last speaker, which is Rosemary Willett from UCL London, and she will actually present really fresh results from the recent Mosaic campaign, which ended last year, which I also participated in. It's going to be really fascinating to see the first results. So she's presenting on investigating Ku, Ka band radar penetration and scattering in an evolving snow depth during the Mosaic campaign. Hello, Rosie.
Hi, everyone. Can you see my screen and hear me okay?
Yeah, perfect.
Okay, perfect. Thank you. So yeah, thanks so much for the opportunity to speak. Yeah, so I'm Rosie. I'm a postdoc. I work for Julianne Struve at UCL in London. And I'm going to be presenting some results from the Cooper instrument, which is a surface-based, fully polarimetric Ku and Ka band scatterometer, which can also operate like an altimeter. And I'm going to talk about some data that were gathered during Mosaic, and I'm going to talk about the scattering surfaces that we see in these data, and also about snow depth determination based on these surfaces. And this is the work of a very large team with contributions from people from all over the world who came together during Mosaic and also afterwards, plus the wider Mosaic team, who I'd like to acknowledge. And as you'll see, it's a very international set of people. So thank you to everyone for their contributions. So I'm just going to start off, and I think kind of we all know this, but I just want to recap because it's so key, I think, for some of the messages in my talk around the typical assumptions that have been used in the past about the dominant scattering surface in the snow on sea ice system. So of course, in the very old days, if you like, the kind of simplest assumption what was used was that for CryoSat 2, the Ku band, the dominant scattering surface was the snow ice interface. And this differs, of course, from the assumptions typically used for Antarctica and IceSat, which was that the dominant scattering surface was the air-snow interface. I should say that for CryoSat 2 more recently, this has been developed somewhat, and particularly over first-year ice, there have been different assumptions used, for example, that the dominant scattering surface may lie closer to halfway through the snowpack. And this is really important for a number of reasons. So just looking at the right-hand side of my slide here, I've indicated some of the things that could occur within the snowpack, which would affect that Ku band radar interaction. So obviously by penetration, we can talk about how well the EM radiation can actually propagate through the snow cover, but the really important thing in terms of where we see power coming back is where that signal is returned from. And that can be influenced by all these different properties. Now, we all know that the Arctic is changing. We know that we're shifting from, or have shifted from a predominantly multi-year ice pack, moving towards a first-year ice pack. And we know that the meteorological conditions, including Arctic warming amplification, different weather conditions and so on, are changing. And all of these changes will, of course, influence the snow properties, which will then in turn influence the way that the radar scattering occurs within that snowpack. So I think this is really important justification for constantly retesting and reassessing these assumptions. And I think that the best way to do that for kind of real certainty is using a ground-based method such as the one that I'll present here. So now I'll talk a bit about the Mosaic expedition. I know some people are very familiar with it and know a lot more about it than I do. But just a brief summary for those who are less familiar, just to say that it took place from 2019 to 2020. And what happened was that an icebreaker ship, along with a whole lot of scientists and instruments, was essentially frozen into the ice pack. So it tracked alongside a particular flow. And the real difference between this and many of the previous ground-based validation campaigns is that it allows us to look at changes over time. So often with a validation campaign, we can go and get a snapshot of a particular location at a particular time. But what this allows us to do is to kind of revisit the same snow and ice over a period of time, and in particular to look at evolution over the seasons. So in my previous slide, I showed some of those snow properties that are likely to influence the way that radar interacts with the snow. Now, of course, it's not just the snapshot in time of the snow that's important, it's the history of the snow, because the history of the snow is what determines the snowpack properties. So this expedition took place over many months, and I'm going to be talking about, in this presentation, data from the winter months. Unfortunately, the stair mode data, which I will talk about, which is illustrated here on the right, which is the altimetric style data, where the instrument was put facing straight down, looking at the snow and ice. Unfortunately, these were only available during winter months, so I won't be able to comment on springtime. But actually, in a way, that's the most useful time, because of course, that's when we're typically looking at satellite radar altimetry data. So to come onto the instrument and talk a little bit about what it is and what it does, essentially, it's fully polarimetric, so it can gather data in all the polarizations, or all four polarizations, if you like. And it gathers data over two frequency bands, Ku band, of course, like CryoSat 2, and Ka band, of course, like Antarctica. The key difference in the data gathering are, of course, that this is a ground-based instrument, so it's close to the ground and it has a small footprint. And the other really key difference is that the frequency bandwidth is much larger for this instrument. So for CryoSat 2 and Antarctica, it's of the order of hundreds of megahertz, whereas for Kuka, the frequency bandwidth, as you can see here, is 6 or 10 gigahertz. And what that gives us is amazing vertical resolution. And that amazing vertical resolution means that we can see surfaces that, although they would be present in the CryoSat or Antarctica data, they wouldn't be resolved. So we wouldn't be able to see them separately. So this is an amazing advantage of having this really high frequency bandwidth. But I will talk a little bit later in my talk about what it looks like when you use Kuka just using the CryoSat and Antarctica frequencies to kind of understand how that matches up. So I think it's also really important to emphasize the differences in the geometry. So as I said, Kuka is a ground-based instrument and it's operating really close to the ground. Of course, satellites are hundreds of kilometers above the ground, and their footprints are of the order of hundreds of kilometers to kilometers in size. And within one of those satellite altimeter footprints, you have really quite high topography of the order of meters, which could include ridges and leads, as well as kind of flat areas of flows. In contrast, Kuka is only 1.5 meters above the snow surface. It has a footprint of about 30 to 40 centimeters, depending on which frequency you look at. And because of the logistics, of course, of deploying a Kuka instrument on a sled, you're not sampling ridges kind of meters and meters in height. You're not able to drive us to do whatever one of those. So you end up sampling relatively flat topography. So I just think it's really important to bear these key differences in mind, and I will come back to them at the end to kind of understand the results in that context. So how can we link these two things? I don't think we can directly say, okay, we see one thing on the ground, so it's going to be exactly the same in space. But what this gives us is an idea of the frequency response. It tells us something about how the frequencies and polarizations respond to these snow and ice conditions. In order to make a full comparison, we would need to do some kind of simulation, and the simulator would provide us with a better, more general idea where we could simulate those geometries as well. So in this presentation, I will make comparisons between Kuka and MagnaProbe data. MagnaProbe provides an indication of the snow depths. I'm going to look at data from two transects, the northern and the southern transect. The northern transect had deeper snow with more snow depth variability, and the southern, shown here in blue, had shallower snow with less snow depth variability. And because they were not time coincident, the Kuka and MagnaProbe snow depths, the coordinates have been mapped onto one another using some software developed by Stefan Hendricks. So first of all, let's have a look at some Kuka data and kind of get a feel for the general characteristics. So what I'm showing in these top two panels here are VV or copol data in the Ka and the Ku bands. Now, the really striking thing is that the Ka and the Ku band data look really similar, and we can see just from looking at this that the dominant scattering surface is the air-snow interface, indicated with the blue arrows, because we know that the instrument is at a height of around 1.5 meters above the air-snow interface. We can also see a trace of what appears to be the snow-ice interface lower down, and I'll talk about that more in a minute. Now let's look at the cross-pol data. So for this one, I've used HV, and I should have said that the VV look very similar to the HH, so I've used VV as just an indication of the copol, and similarly, the HV look very similar to the VH, so I've used HV as an indication for cross-pol data. So looking at these bottom two panels and the cross-pol data, we can see that what now appears to be the dominant scattering surface is the snow-ice interface. So this is very interesting. I don't think there's been a lot of information previously on cross-pol data from a ground-based instrument. And this is very exciting because it provides what appears to be a very valid way of understanding where the air snow and the snow ice interfaces lie. Interestingly, not really in the way that we expected. So of course, previous studies have looked at different frequencies, but here actually it looks like the different polarizations are going to provide really interesting insights. So this is just an example of some Ku-VV band data, and the top panel just shows the data. The middle panel shows some peak picking that I've done. So this is a beam limited system, which means that the maximum peak appears at the range of where most of the scatterers are. So hence a peak picking as opposed to a threshold retracking approach is appropriate for a beam limited system. And what you can see in the middle panel is that the purple dots appear to track the air snow interface, and those are the peaks that I've picked that are above a certain threshold at the smallest range, so if you like, highest in the snowpack. And then the red dots appear to track the snow ice interface, and those are the peaks that I've picked that are deepest in the snowpack. So those are the ones, if you like, the furthest away from the antennas. And what I'm showing in the bottom panel is if I overlay the maximum peak. So if I say, okay, but what is the highest peak for each echo? And what we see is that actually in most cases for the Ku copol data, the maximum peak is coincident with the first peak. Sometimes it's coincident with the last peak, but that's actually in a minority of cases, less than 20%. Whereas, and I'm just going to do something a little bit simpler for the cross-pol data, just for the purpose of this presentation, to show that the maximum peak appears to track what we think is the snow ice interface in the cross-pol data, which kind of goes with what we were seeing before. So what I show here is I've just combined some echoes and I've also plotted the MagnaProbe snow depths on top. And the way that I've done this is that I've divided every transect into mini sections of just a few meters, and I've looked at the average echo and I've looked at the average MagnaProbe snow depth in order to be able to compare the two. And what I'm showing here, so there's a lot of information, so just to keep it simple, if you could draw your eyes down to the black line and the kind of beige yellow line, those are tracking using my peak picking algorithm the bottom of the snowpack or the snow ice interface, and I've overlaid on top of those in white the MagnaProbe snow depth, and you can see that visually there's a very good agreement between where the MagnaProbe thinks the snow depth is and where Kuka thinks the snow depth is. What I've done with the MagnaProbe data is I've just scaled them by dividing them by 0.8, and that's to account for the reduced radar velocity in snow, which of course is a really important thing to account for because the radar travels more slowly than in free space. So here what I'm showing, moving from left to right, is what happens if I increase my averaging length. So you can see that I've called it bin size. This is just the length along the transect along which I average. And what you can see is that there's really good agreement between the MagnaProbe snow depth and the Kuka-derived snow depth, even at an averaging length of just 3 meters. And you can see that it increases as I increase the averaging length up to 50 meters. So I'm going to talk a bit now about whether that makes sense and what that looks like in the context more broadly of what the snow looks like. So this is some work done by Lu Zhu, who came to do some work with Julian at UCL. And what you see here is I'm just showing some variograms. And if you see these plots, you can see that the variogram in the top right, which indicates the kind of lag distance. And we can see that over kind of between about 25 and 50 meters, we can see that kind of really starts to plateau. If I then plot the R value, so this is the R value of the agreement between the Kuka-derived snow depths and the MagnaProbe snow depths, and I'm plotting that against bin size, so it's not really a variogram, but it sort of looks like one. And you can see those same kind of characteristics where between kind of 25 and 50 meters, you get this kind of plateau. So that kind of makes sense based on what we know about the snow characteristics, just looking at the MagnaProbe data. This is doing this a different way, so this is the same type of analysis, but this time instead of looking at the first peak and the last peak in the KU band data, what I'm looking at here instead is I'm using the KA band co-pol data to tell me where the air snow interface is, and I'm using the KU band cross-pol data to tell me where the snow ice interface is. And you can see this similar kind of good agreement with a similar pattern of improvement as the bin size increases. And you can see that we get up to an R value of about 0.86 at a bin size of 50 meters. I think this is kind of remarkably good, especially given that Kuka and the MagnaProbe are not measuring the exact same snow locations. So we all know that snow depth can vary over very small length scales, and because of the challenges of gathering MagnaProbe and Kuka data in the dark over kind of kilometers of transect, so of course the measurements are not perfectly spatially coincident. I think this is a really encouraging result in terms of the ability to determine these surfaces in the Kuka data, and in terms of the ability to then use them to determine snow depth. So I said at the beginning I'd talk a little bit about what happens when, instead of using that wonderful kind of enhanced vertical range resolution we get from the large bandwidths that we have with the Kuka instrument, what happens if we essentially downgrade that, and in the post-processing of the Kuka data, we only take the frequencies which are included in the CryoSat 2 and Antarctica bandwidths. So these plots on the left show what happens. So the solid lines show the full frequency and the dashed lines show what happens if I instead convert this to CryoSat 2 and Antarctica. So it's as if we had CryoSat 2 or Antarctica frequencies, but operating on the ground from Kuka. Now, what you can see is, of course, those peaks get very broad. So it's no longer possible within a single echo to determine different surfaces. Although I think it's really important to say that that can still pull, if you like, the peak location to one side and another. So just because something can't be resolved doesn't mean that it doesn't have an effect on the peak range, but it means that the effect on the peak range, if you like, is more subtle. So it's not possible to resolve it, but it can move it. And obviously, a lot of the work that we've seen this morning is kind of relating to that change in the echo shape and the change in the peak location of the echo. So if we use this technique, because we can't resolve peaks within one echo, we're left with the polarization work. So again, here we're using polarization, so using the KA co-pol data to tell us where the air snow interface is, and using the KU band cross-pol data to tell us where the snow ice interface is. And we actually get almost exactly the same results. So this is really interesting, and it's quite interesting in the crystal context. I know there isn't a plan to include polarization within crystal, but it definitely gets us kind of thinking about the role of potential polarization indications for future missions. I will come on to that again in a little bit more detail in a minute, but I did want to show this result based on just using those frequencies. Just to highlight really briefly some work that a fantastic master's student has been doing here at UCL using an AI approach, and what we did was to feed the AI system a combination of co-pole and cross-pole echoes, where we tried to combine them in such a way that the air, snow and snow ice interface had similar magnitude peaks. And very interestingly, the neural network was able to, using the MagnaProbe snow depths and those echoes that we fed it, was able to track fairly effectively, shown here in green, the snow depths as compared to the MagnaProbe snow depths as shown in blue. So there is the potential for an AI approach to also be quite good at doing some of this this peak picking and determination, and that's something we'd like to do some more work on. That was a very interesting project. Really excitingly, just in the last week, we've had Thomas Newman has been doing for some time now some great work deconvolving these data. And I just wanted to show you kind of the improvements that we can see in the deconvolved data. So looking at the left two panels, these are Ka band cross-pole data. So interestingly, you know, always the assumption with Ka band was that there would be very little penetration through the snow, and what you can see is looking at the Ka band cross-pole data, you're definitely seeing the snow ice interface here, and it actually appears to be the dominant scattering surface. So the deconvolution from top to bottom really improves our ability to understand where the air-snow interface is in the Ka band cross-pole data. And then on the right-hand side, looking at the Ku band co-pole data, one very valid question that I've been asked a number of times is, are your snow depths, are they really just side lobes? So I didn't think that they were side lobes because they were variable, and of course side lobes occur in a kind of predictable position, but the deconvolution gives us real confidence that that's definitely not the case. So this is a really nice piece of work that Tom's been working on using a variety of different deconvolution techniques, and he plans to publish something on that. So if you are interested, yeah, stay tuned for his paper. Vishnu Nandan, who I work with really closely at the University of Manitoba, has also done some wonderful work translating our code from IDL into Python, which has given us fantastic flexibility in terms of what we are able to do with the code. So that's another really exciting development that we've had in quite recent times. So just to kind of summarise, going back to the idea of dominant scattering surfaces. So the big question in my mind is why? Why are we seeing from KUKA that the Ku band appears to have a dominant scattering surface at the air-snow interface most of the time, whereas multiple studies using satellite altimeters indicate that may not be the case. So I think the really important thing here is something that I think Stefan actually mentioned in the chat, which was around the contributions of flat surfaces versus ridges. Those very different footprints where you've got kind of very high topography. Is it possible that the flat surfaces are being sampled preferentially from a satellite altimeter? Is it possible that the relative roughness, so if the air-snow interface is relatively rough compared to the snow-ice interface, could CryoSat-2 preferentially therefore be sampling the snow-ice interface because of that, and therefore not seeing, if you like, because of the phase behaviour, the air-snow interface so well in its data? There was also a really interesting suggestion that I picked up at EGU around the coherent backscatter opposition effect, which relates to the distance between the two antennas receive and transmit on the ground versus the air. So there are a number of avenues to explore, and I think really some type of simulation is absolutely needed to try and make more sense of this. But I think that KUKA does at least indicate that Ka band can penetrate into the snowpack. Ku band doesn't necessarily, and it definitely does see the air-snow interface at these kinds of frequencies. And I think there's a lot of discussion around crystal and best ways to combine the frequencies to determine snow depths and interpret crystal data. Thank you very much. Any questions? Happy to take them, or feel free to drop me an email. Thank you.
Wow, Rosie, thank you so much. Amazing. I was so enthralled. I wasn't actually even looking at the chat, which is what I'm supposed to be doing, to look at questions. Well, the deconvolution work looks amazing. Of course, I'm biased, but that was going to be my question. So just to confirm, so the earlier results that you showed with the correlation studies, that was prior to deconvolution, is that right?
That's correct, because that's what I had available at the time. So what I would really like to do, of course, is to now go back and do some of that work with the deconvolved data. Based on what I've seen so far, I don't think it's really going to change the main conclusions. It's not going to suddenly put interfaces in different places. If anything, it confirms that what we thought we saw, we do see, which is, of course, important. But what it does is, because it reduces that noise and the things that are not real, it gives us real confidence about the things that we do see. I think the result for the Ka band cross-pole data is kind of amazing, that even though the Ka band is always assumed, you know, very much to not penetrate the snowpack, and this supports some work that Isabel Lawrence did, seeing that actually, you know, Ka band may penetrate the snowpack, and actually we saw that in some of the talks earlier today, that possibly that could be the case. So it just gives us kind of more scope, and it's an incredibly rich data set. So I hope to publish something on this really soon, but I think there's a lot more that we can do with it, and hopefully it will be very useful. You know, I think Kuka is an amazing tool for validation. Hopefully it will be used for many more validation campaigns, because it has these two very useful frequencies, plus the ability to, you know, decrease that frequency band, so that we're really looking at CryoSat 2 and Antarctica frequencies only.
Exactly. No, incredible work, really rich data set, as you said. And Rosie, yeah, thank you so much. As always, really critical work that you're doing here to help us interpret the satellite data. Okay, so Robert, I hand it back to you for any final comments. Thank you.
Yeah, thanks again. And as Sinead said, that this is really amazing work, and I'm looking forward to see some new results from that. Yeah, thanks again for all the 5 speakers. It was really nice to have you here, and I think we saw like a broad variety of research regarding CryoSat 2 and applications. So that was very nice. And I'm looking forward to see all of you in person again, maybe next year it's a Living Planet Symposium then. So let's hope for that. And yeah, otherwise I think we now have a coffee break. And then it's going on with ocean and marine gravity. And at this point, I actually also want to thank Matteo again for the support in the background. So that should be acknowledged as well. And yeah, so then just enjoy the coffee break, and